busy on Zoom today. All right, let's go. So first things first, we just had a video. It's from an old version of the textbook, so it's called chapter 5, but they just kind of rearranged some stuff. And so it is chapter 7 that we're going through. And I made you watch the whole thing, I know. But that means that we can review paired data and 2 independent sample means today. And so today I've prepared for you some practice problems. Okay. And so it does assume that you've watched the video. Of course, I've also posted a lot of stuff. So I want to talk you through that. So there's the link. I don't have a pointer on this here, but there's the video and then the notes from the video and an assignment for 2 samples for the mean. And then this is the inference for numerical data practice that I am going to go through today, and I'm going to save it. Come on. Put her there. Nope, there. Okay, go back here. I also, because that's the end of chapter 7, which is actually the end of inference that we are going to do, I do want to post a bonus assignment on ANOVA, just like we did for chi-squared. We can compare more than 2 means, right? What if I have 3 or more means, right? Averages across more than 3 groups, or 3 or more groups. And so that's called an ANOVA. We're not going to do that in this course, but I think you've got the skills and you can do it. You can plug through it as a bonus assignment. So I'll post that. But I also posted this inference decision tree, because although we'll see a little bit more inference in regression when we do lines of best fit, this is kind of the end of the meat and potatoes of inference. So congratulations, did it. So first, you're going to ask yourself, well, what type of question do I have? Is it a proportion question or is it a means question? And then if you have 1 sample, got all the assumptions that you have to check and stuff like that. And so might be helpful for you to make your own kind of decision tree like this, or you can use mine. But of course, the creating it is very valuable as well, right? Because that helps you kind of tease out some of the differences. I do have the ANOVA for 3 or more groups down here, but you can ignore it. I also posted the Word document in case you want to muck around in there. I made it in Word so that you could, although I hate Word, so. And then sat down last night, like, okay, let's see what's going on here. We have a test on Tuesday, and I bungled it. I posted the practice 4 test 2. It is incomplete until I get to my office and I add some questions on chi-squared, test of independence, and 2 sample means. I didn't have time to do that last term, but this term we do. And so for now, it doesn't list 2 of the types of problems, right? But it is practice, so you can do it. And then I'll kind of squeeze in the other 2 types on here and add them to the end and then just kind of append them. Okay? And so what I want you to do is, as you read each type of question, I want you to figure out what type of question it is, right? What's the header on your formula sheet that you're going to be looking at? Okay? And did I start this? Oh, phew. Just having a day. I was saying that in my first class, and they were saying that they were also, everyone's just kind of feeling weird today. I don't know. Maybe it's just me. Maybe they were just being nice. I'm having like a super weird day. But anyways, so I posted the practice, posted the solutions. I'll update it with more practice. But for now, that's good enough because we've got I always feel at this point in the term that I'm like, oh no, things are moving way too fast. I'm just getting to know these guys. And then it's all downhill from here. All right. So then we do a little bit of line of best fit stuff and then final exam. We're done. Okay, let's see here. So today, as a way of reviewing 7.2 and 7.3, we're going to do examples. Now, I used to have a platypus test. I like to make my my all tests themed, and I pick animal themes because it's easy to find fun facts about them. But the platypus is way too creepy, so I cut it. I use it for practice tests now. And then someone was like, oh, is it because the animal doesn't start with M that you don't like it? Because I have a manatee test, of course. I have a meerkat test. I have what else do I have? I have so many more. But now I'm blanking. Anyways, that kind of a day. I have a magpie test. They're cute. I'm tempted to just stick with the manatee this term. Never had a manatee test 2. Only a manatee test 1. Or do you want a new animal? But the criteria is it has to start with M. I don't have a monkey one, but I feel like monkey is too broad. My own problems. All right. Let's see here. Better. Anything in italics is kind of extra. Yeah. Yeah. Manta rays. Okay. Love it. A little bit more fierce. Maybe. I'm going to learn so much about manta rays. I feel like, yeah. Oh, I have a moray eel exam that I could dust off. But manta rays. I don't have a moose one. So there's that. I've got some M animals, but I'll have to add manta ray. Oh, someone was like, why don't you do a mongoose? Anyways, it'll be a surprise. What animal will it be? Has to start with M, I guess. The platypus. The first scientists thought it was a hoax. Anyways, it's got the duck bill and web feet. It's got the beaver tail, and then the otter body and fur, and it's all just kind of. But the key part is that the males are also venomous, and so they have sharp stingers on the heels of their rear feet, and they can use them to deliver a strong toxic blow to any foe. Clearly copied from somewhere. So here's my question. You overheard some people talking, and they're saying that the platypus releases different amounts of venom if he's provoked and angry, which we'll call angry, than if he's startled or cornered, which we'll call scared. There. Naturally, you decide to test this theory with a sample of 32 randomly selected platypuses. You decide that they will all receive both treatments, Some will be scared first and some will be made angry first. How cruel. It's obviously made up, don't worry. And this assignment will be done randomly. The amount of venom secreted after each treatment is measured in milliliters, and a summary of the data you collected is found below. So we've got scared, angry, the difference. That should be a really good clue as to what type of question this is. Why? Because we're taking two measurements on the same platypus, right? And we're analyzing the difference, which tells me that this is going to be paired data, right? And so this is a paired samples. Paired samples or matched pairs. I like to call it matched pairs or paired samples. What do I call it on here? Paired data or matched pairs or paired samples, I guess. This is that sneaky one where if we imagine our spreadsheet, I've got my platypus, 1, 2, 3, blah, blah, blah. I have a measurement for when they're scared. I have a measurement for when they're angry. They were both scared and angry at different times, and we measured. And we also then have the difference between the two. Now the difference becomes one column, right? One sample of differences, right? And that's the beautiful thing about paired samples is now you just have one sample of differences, right? And so here, this is two samples, but it's a special case because I've made two measurements on the same platypus, right? Okay, so the type here. Is paired data or matched pairs or paired samples, anything to indicate to me that you know it's for the mean difference. And I'm going to need to copy this, I guess. Put it on a new page here. Oh no, no lines. Hate that. We're going to be doing a lot of writing today, so I think I need to unhook it for a second here. Template settings, lines, apply. I have no idea why it won't let me do it while it's hooked up, but it doesn't. Okay. So when you're reading the questions on the test, right, the first thing you're going to do is figure out what type of question you have, and then that will determine where you are on your formula sheet. So on your formula sheet here, you've decided that you have paired data or matched pairs, which you don't really need the formulas for because it is just a one sample mean problem. It's just that the mean is now for the differences. So when I talk about the differences, usually I indicate that with a little mu diff, x bar diff, n diff, s diff, right? It's just extra, but it's nice to emphasize it. Is there evidence that platypuses do in fact excrete different amounts of venom depending on if they're provoked or angry? Then if they're startled or cornered, scared, use a 95% confidence interval to test the hypothesis. So we can build a confidence interval to test this hypothesis. Okay. All right. We're going to build a confidence interval. We need the mean of the differences. This is a sample mean of the differences. So we're given, given the x bar of the differences is negative 0.50. And S of the differences is 7.51. How many differences? I think there were 32, right? 32 randomly selected platypuses. And it's fun to say platypuses. And I looked it up. It is platypuses. So, but I looked it up a long time ago when I made this question. Close to, probably 10 years ago now. So, might have changed, I guess. So what do I need? Well, if I compare to what I have to what I need in my formula, I have x bar diff, I need my t star, and this subscript n diff minus 1 is really just the degrees of freedom, so you can ignore that. But I do need a t star. I have s diff and I have n diff, and so t star requires the degrees of freedom. The degrees of freedom is n diff minus 1, which is 32 minus 1, which is 31. If we go to our table, though, I know it stops moving up by 1 at 30. And so I'm going to clarify, but using degrees of freedom equal to 30 on the table. Because if I go to my table and I try to find 31 degrees of freedom, I know it starts moving by tens instead of ones, and so I'm going to use 30. We wanted to build a 95% confidence interval. Which means t star is 2.042. Roughly 2, but a little bit bigger. 2 point, therefore t star is 2.042. Now, I can put this together, x bar of the differences plus minus t star. I'm just going to write t star. You can add at n diff minus 1 degrees of freedom, but you don't have to, times s diff over the root of n diff. A couple of words of caution here. Sometimes people get caught up on the 30 degrees of freedom, but that's not your n. Your n is still 32, right? So we've got negative 0.50 plus minus 2.042 times s diff 7.51 divided by the root of 32. Do a little bit of math. .51 divided by the root of 32. Let's start there, times 2.042. I get a margin of error, negative 0.50 plus minus 2.710944869 milliliters. So I can build my interval. Let's just round this to 2.71. I've captured a lot of activity. Not a lot happens after the 1. And so -0.50 plus minus 2.71. -0.50 minus 2.71. I get -3.21 up to -0.5 plus 2.71 up to 2.21. How do we use this? Well, first, let's interpret the confidence interval, right? That's always part of making a confidence interval. And so now, what do we need to be really careful about? This is for the mean of the differences, right? So we are 95% confident the interval from -3.21 to 2.21 captures the true mean difference in venom excreted when angry versus scared. From the mean of the differences, I see that scared is less than angry. And so the difference, I can kind of reverse engineer this and say that the difference must be scared minus angry to get a negative. One of the things to note is that notice that the standard deviation doesn't have that same relationship just because of how standard deviations work. But the means do. Okay, so it's scared minus angry. When scared versus angry, right? We could talk about -3.21 is 3.21 more when angry than scared, right? If you want to talk about it that way. Yeah. But as long as you talk about the true mean difference, that's fine. So if the true mean difference could be 0, right? So we want to test the null hypothesis that mu diff is equal to 0. In fact, if we want to know if they excrete different amounts, the alternative hypothesis that we're testing is that mu diff is not equal to 0. What's nice about paired data or matched pairs is that you're always comparing the mean difference to 0, right? Because if the mean difference is 0, then, or is reasonably 0, then the two groups are the same and there's no difference between them. So what we're going to do is we're going to use, I like to use a number line. I found an interval from -3.21 up to 2.21, but a difference of 0 is reasonably in there somewhere, right? If I go from a negative to a positive at some point, I cross 0. And since 0 is one of the possible values for mu, then that means I don't have enough evidence to reject H0. If we found that the entire interval was below 0, for example, that would mean that you have enough evidence to reject H naught. But since mu diff equals 0 is in the interval, a plausible value of mu diff, right, is what that really means. That's what the confidence interval tells us. So 0 is one of the possible values, is in the interval. We do not have enough evidence to reject H naught. Which means that there is not a significant difference in the amount of venom excreted. Therefore, there is not a significant difference in the amount of venom excreted when scared versus angry. Oof. Back in the day, I used to be so mean, and I would always make my students do both a confidence interval and a hypothesis test for every question. Now I'm nice and I just pick one of them. But you have to be prepared for both. So it's still kind of mean, I guess. But you need to be prepared. We've already done part of this question though, so you can go ahead and do a formal hypothesis test, which means following all the steps. And so is there evidence that platypuses do in fact excrete different amounts of venom depending on if they're provoked or angry than if they're startled or cornered? Use a formal hypothesis test with an alpha level of 0.05. We should check our conditions, but the conditions for numerical data is not very interesting, right? If we have a sample size larger than 30, we can assume normality. And so that's kind of, they were randomly selected. Okay, fine, conditions. I should have done it earlier, I guess. Random, check, n is 32, which is greater than 30. Therefore, we can assume normality. Cheeky. So conditions are a lot easier for numerical data because that's it. Right, the first one, the random selection of the platypuses, as well as the random assignment of treatments, preserves independence, and then we have to check normality, but because we have a large enough sample size, we can just assume normality. So then, step 1 is to state the hypotheses. Which we already did. So I'm going to squeeze them on here. Mu diff is equal to 0, and the alternative is we want to know if there's different amounts, but we already used that, not equal to 0. I will make a note that this is a two-sided test, right? Because I care about either direction around 0, so just not equal to 0. And so I make a note here, this is a two-sided test, right? Or a two-tailed test. Step 2, do the test. Do the do. Calculate the test statistic, but that's so boring. From your formula sheet, we know that T is X bar of the differences minus mu diff divided by S diff divided by the root of N diff. What's really nice about paired data is that you know the null hypothesis is exactly what's on your formula sheet. You don't need to make any changes. Once you've decided that it's paired data, that's what you're going to use. And then it's just the sign in the alternative that could change. Right. Makes it a little bit harder though, because you have to think about how the differences would behave. Not hard, but you have to kind of think about it. So now, in terms of kind of checking for reasonable answers, from the confidence interval that we just did, do you expect a big T or a small t? I'm expecting a small t, right? Because I don't have enough evidence to reject H naught. I already know that about this question. And so I'm expecting my t to maybe be around 1, but not past 2, right? Because 2, I would start rejecting H naught. So it's always good to have an idea of kind of what a reasonable answer would be before you do it. Negative 0.50 minus 1. How far is negative 0.50 from 0? Taking into account the spread of 7.51 over the root of 32. The standard error. Negative point, maybe I'll start with 7.51 divided by the root of 32 first. And I think we're at the point where we can just go for it. I get approximately negative 0.3766214547, which confirms what we were saying, right? I'm not expecting this negative 0.5 to have moved that far from 0 because I already know I'm not going to reject H naught. So now, step 3 is find the p-value. We've matured so much at this point that you might prefer the critical value approach. What's the critical value approach? In this case, you're welcome to use it. I'm not going to, but we were told to use an alpha level of 0.05. So, and we also know from earlier that we have 30 degrees of freedom still. Right? I know I have a two-sided test. So what if I force this two-sided P to be 0.05, right? The alpha level. Then, in order to be able to reject H naught, my T would need to be larger than 2.042. Okay. So that would be if you wanted to use the critical value approach. I will not, I'll keep it on here though, because what am I going to do? I'm going to take this and I'm going to try to place the absolute value of T, but T was 0.3 something, right? Very small. And so what I'm going to do is I'm going to grab a little bit more, not much copy. I'm going to bring it in. For critical value, which would be 2.042 at 30 degrees of freedom. And so here, first, let's pretend we haven't done all the work earlier using degrees of freedom equal to n diff minus 1, which is 32 minus 1, which is 31, but using degrees of freedom equal to 30. That's the same blurb as before. You have to tell me that, yes, you know how to find the degrees of freedom, and yes, you know to round down in the table if it's not exactly listed, right? So two things that you're kind of checking off the list here. But now I want to try to place the absolute value of this thing on the 30 degrees of freedom line. And I find that the absolute value of t equal to negative 0.3766 is between here and here. On the upper end, I have 0.683. On the lower end, I have 0. Right? 0 is always the center for t, right? I have a two-sided test, which means that my two-sided p is somewhere between 0.5 and 1, right? If I'm at the center at 0, then how much area do I have in both the tails? I would have 1, right? So here, this becomes 1. So the two-sided p is going to be somewhere between 0.50 and 1. Big. And if the p is low, the null hypothesis must go, but it's not low. In fact, it's very large, which means in our conclusion, step 4 is our conclusion. We always use the same blurb, right? First, you're going to compare your p-value to the alpha level, right? Since our two-sided p-value is between 0.5 and 1, it is not less than the alpha level of 0.05. Yeah. So since the two-sided p is between 0.50 and 1, it is not less than alpha equal to 0.05, which means we do not have enough evidence to reject H naught. Which means we do not have enough evidence to reject H naught. Therefore, there is not a significant difference in the amount of venom excreted. There is not a significant difference in amount of venom excreted. Same thing that we found earlier, just two different ways. Luckily, they back each other up. There are rare instances. So when we use a confidence interval to test the hypothesis, it will be a two-sided test just because of how intervals work, right? Confidence intervals always leave area in both the tails. And so it'll only correspond perfectly to a two-sided test. And there are kind of rare instances where the one-sided test might not match up with your confidence interval, but it's because it's a one-sided test. Okay. Let's see here. Question 1. Question 2. I have to remember what the questions are about. Any questions about question 1 though? Nope. Okay. Someone cracked a joke saying that platypuses are even slower than manatees. Naturally, you decide to analyze the validity of the joke because why not? You randomly select 200 platypuses. You want to be really, really sure, right? So 200 platypuses and record their speeds. You find the mean speed of these platypuses to be 3.6 miles per hour with a standard deviation of 3.1 miles per hour. So now I have a mean and a standard deviation for the platypuses, but then I also have you randomly select 156 manatees and find their mean speed to be 3.9 miles per hour with a standard deviation of 2.8 miles per hour. Okay. Is there evidence that platypuses are even slower than manatees? We're going to use a formal hypothesis test with an alpha level of 0.1. Okay. What type of question is this? I've got platypuses, I've got manatees, I have a mean and a standard deviation for both groups. So I've got 2 independent sample means because these are measurements on platypuses and there's no natural way to link them. Okay, you're going to be matched with this manatee, right? And that's okay. We just take a step back and we compare them as 2 independent groups. And so the type here, kind of most importantly, is 2 independent sample means. I like to throw the word independent in there because it emphasizes to myself mostly that, okay, these are 2 independent groups. I'm going to treat them as 2 independent groups. But really what I want to do is I want to compare 3.6 miles per hour to 3.9 miles per hour, taking into account the spread of both of those groups, right? And so once I've decided what type of question I have, I go to my formula sheet and I snag what I need. The 2 sample means or 2 independent sample means looks like this. We can build a confidence interval or we can do a hypothesis test. This is very similar in layout to when we did 2 sample proportions, right? I think it's easier to talk about mu1 equals mu2 because then you can easily compare them in the alternative hypothesis. But technically, we are testing mu1 minus mu2. How does it compare to 0, right? Whichever one you prefer, fine by me. And we use the simplified version of the degrees of freedom is the smaller sample size minus 1, right? So even though there is a huge formula that we could use for the degrees of freedom that software uses, but we don't because we're just working by hand. Well, I want to do a formal hypothesis test, which means I'm going to be down here. Our conditions are the same. We just test it for both the groups. I think I randomly sampled both groups. So let's just get the conditions out of the way. We randomly sampled both groups. N1 is 200, which is greater than 30. And N2 is 156, which is greater than 30. So we can assume normality. And found the two groups are independent of each other. But we take care of that condition in picking the type of question, right? Are independent. That should have been up here, I guess. For the proportions, I will, because we spent a lot of time on it, but it'll be a series of check boxes and you check the ones that would apply. Yeah. And it's just 1 mark and then then you can move on. So you have to know which ones you would check in general for that type of question that you're about to do. But for numerical data, because it is so kind of easy, I guess it might be nice to have it on there. Check that it was randomly selected. Always check the randomly selected box. That's always a condition, right? Random check, great. Half a mark, done. And then whatever else applies is usually how it goes. And then if the sample size is greater than 30, we can assume normality, and that's good. Maybe on test 2, I'll have the conditions for you to check off for all the questions, and then on the final exam, we can go a little bit easier on it. How about that? Okay. Hypothesis test. Step 1. State the hypotheses. Now, like I said, it's kind of a choose your own adventure. They mean the same thing. If mu1 is equal to mu2, then of course mu1 minus mu2 is equal to 0. Right? They mean the same thing. So whichever one you like, you should use that. I tend to gravitate towards mu1 is equal to mu2, but I'll do both. H naught. Now, when we're talking about 2 groups, just like we did for proportions, I want to see question-specific subscripts, especially in your hypotheses, right? Mu1, mu2 doesn't mean anything to me. And so I want to see mu p and mu m, right? Platypuses and manatees. So mu p is equal to mu m. Must use question-specific subscripts. Because that becomes important when we want to actually test the hypothesis. So is there evidence that platypuses are even slower than manatees? Meaning, my alternative hypothesis is mu p is less than mu m. Right? If you just had 1s and 2s on there, that doesn't tell me anything. And it's just good practice to have the question-specific subscripts. You could define it somewhere else. Let 1 be m and let 2 be platypus or whatever. But to save yourself as many marks as you can, because sometimes I don't see that, right? I'll be looking for the question-specific subscripts, and if I don't see it right away, you lose marks. So you're safer to just have it here. Okay, or you only have to do one of these, right? Mu p minus mu m is equal to 0, but the reason I find that this one's kind of tricky is if you want to show that m is bigger than p, then you need to think about p minus m. So think about 1 minus 2, for example, just kind of plugging in fake numbers. You get a negative number, which means it would be less than 0, right? Or you could take it from here, but why wouldn't you just keep it here then and subtract it over So this is why I don't love this setup, because it's not as intuitive. But doesn't matter. Either way, it's a one-sided test. I make a note of here. We don't need it until way later, but nice to know. Step 2, do the test. It's bigger, but not that big. What's nice is we skip the pooled standard deviation. We can't, there are formulas using the pooled, but I don't like it. So we use this one here, x1 bar minus x2 bar, s1 squared over n1. Just remember to square those standard deviations and then divide by n, and then add them up, and then take the square root. x1 bar minus x2 bar. Here, it gets way too boggy if you write it with question-specific subscripts. So here I kind of, I ease up on that. As long as you follow, right, the same order, 1, 2. S1 squared over n1 plus S2 squared over n2. Let me see if I have all that information. 3.6 and 3.1 for group 1. 3.6, 3.1 squared over 200. Group 2, the platypuses, sorry, the manatees, 3.9 with a standard deviation of 2.8. There. This is the standard error of x1 bar minus x2 bar. So if you've shown your work, now I'm not going to make you do this on the test, but just in general, right? If you have to, if you read ahead and you see, okay, I got to make a confidence interval, then as long as you have this work shown here, then you can just pull it into the confidence interval, because unlike proportions, the confidence interval and the hypothesis test use the same standard error. So that's nice. Saves you a little bit of work. I get, well, let's start with 3.6 minus 3.9, negative 0.3, and then 3.1 squared divided by 200. And I'm going to store that so I can keep it. Do 2.8 squared divided by 156 plus recall A. And I get the square root of 0.09830641026. I'm going to take the square root of that. Point 3135385307, and this is the standard error of x1 bar minus x2 bar. I'm going to store this in A on my calculator, just in case I need it later. which I guess I need it now. Negative 0.3 divided by that answer, but let me just make sure it had the right answer. Negative 0.3 divided by shift recall 8. Okay, good. T is negative 0.956822021. Find the p-value. Could find the critical value here, right? Remembering that alpha should be 0.1 because we were given the alpha level of 0.1. So, but we'll use the p-value. First, using degrees of freedom is the minimum. So the minimum function of n1 minus 1 or n2 minus 1. It's really going to be the smaller of the two sample sizes minus 1. But how we're going to write that is the minimum of 200 minus 1 or 156 minus 1, which is the minimum of 199 or 155. Well, the minimum of those two is 155. We don't have a 155 degrees of freedom line on our table, but so but using degrees of freedom equal to, now remembering you have to go find it, and you always have to round down. So we'll use 100 degrees of freedom. Bring that in. Degrees of freedom equal to 100 on the table. So now I try to place my t that I calculated. I need to take the absolute value of it, and I have the absolute value of t equal to negative 0.9568 is somewhere between 0.845 and 1.042. Which this is where I need to remember if I have a one-sided p or a two-sided p. So we can go all the way up to your alternative hypothesis. I only care about one extreme. So I have a one-sided test. So the one-sided p is between 0.15 and 0.20, being really careful that you write those in the correct order, right? You could switch the signs and write them in this order, but it gets kind of weird. Usually we like to read things from smallest to largest. And so I encourage you to just use the same signs, but then switch the p-values because they'll be decreasing as you move out into the tails. So we've got a relatively large p-value. We want to compare it to 0.1, right? And so in our conclusion, step 4, our conclusion, since our one-sided p or p-value is between 0.15 and 0.20, It is not less than the alpha level of 0.1. It is not less than alpha equal to 0.1, which means we do not have enough evidence to reject H naught. To reject H naught. Therefore, there's not a significant difference in the speeds, in the mean speeds, or how is the question worded? You take the question and you reword it as an answer. There is not evidence that platypuses are even slower than manatees, or some version of that. Therefore, there is not evidence platypuses are slower than manatees. Is that here? Just gonna mute everyone, just in case. I couldn't really tell if it was here or there. Okay. Let's see here. What's the follow-up question? Probably a confidence interval, because that's just how I roll. Is there evidence that platypuses are even slower than manatees? Use a 99% confidence interval to test the hypothesis. Oh, my screen just got dark. Knowing what we know from the previous question, do you expect the confidence interval to include 0? Yes, because we didn't reject H naught earlier, and so 0, a difference of 0 is a plausible value for the mean of the difference in the means. So, but we'll go ahead just for practice building the confidence interval. There's no harm in that. It'd be more interesting if we had rejected H naught, because then a natural follow-up would be, okay, well, how much faster or slower or whatever. Now, when we did a one-sided test with an alpha level of 0.1, right? So just as a side note here, note a one-sided test with alpha equal to 0.10, it would correspond to what confidence interval would correspond to, I'm forcing the area in one of the tails to be 0.1, but to make an interval, I would also need this area to be 0.1. This would correspond to an 80% confidence interval. Those results would match. Which we can check against our table, right? If we force our one-sided P to be 0.1, and then I need to draw here so I don't lose track. Matches an 80% confidence interval. Right? Now we're going to build a 99% confidence interval. Okay, so basically what we said is that an 80% confidence interval would include 0. So if you went out even wider, you really expect it to include 0, but let's just do it just for practice. Okay. The confidence interval x1 bar minus x2 bar, and maybe I'll change these to p's and m's, plus minus t star times the s1 squared over n1 plus s2 squared over n2. I guess 1 p m. But we already found this. This is the standard error of x1 bar minus x2 bar, which is, what was it? 0.313538. I stored it in A. From earlier, we already did this work here. That's what's nice about when you get to do both, right? You can just recycle some work. In fact, we even know what this difference is, right? It's the same as the numerator in your t. 3.6 minus 3.9 is negative 0.3. I'll write it out though. 3.6 minus 3.9 plus minus t star. We still need that t star, but can I do this? Let's get weird with it. Store A. I stored it in A on my calculator. Or you can just enter these values if you want. But we need, so negative 0.3 plus minus t star times whatever is stored in A. T star for a 99% confidence interval at degrees of freedom equal to, let's just for practice write out that minimum function so it's not so bulky looking anymore. Minimum of n1 minus 1 or n2 minus 1, which is the minimum of 200 minus 1 or 156 minus 1, which is the minimum of 199 or 155, which is 155, but using degrees of freedom equal to 100, because we already talked about that. So then T star from the table, don't want the 80%, I want the 99% confidence interval. So my T star at 100 degrees of freedom is 2.626. Now we're ready. Negative 0.3 plus minus 2.626 times whatever is stored in A. Shift recall A times 2.626. I get negative 0.3 plus minus 0.8233521.817. You check to make sure you get the same thing. You can round that a little bit, talking speeds. So 2 decimal places is probably fine. So, or negative 0.3 plus minus 0.82. Negative 0.3 minus 0.82. Negative 1.12 up to negative 0.3. Do you expect it to be positive or negative? Positive. 0.82. Up to 0.52. We are 95% confident. Whoa, thank you. I feel like you caught it early enough. I don't need to write it in red, right? Thank you. 99% confident. The interval from negative 1.12 to 0.52 captures the difference in mean speeds. Captures the difference in mean speeds. Between E and M, just because I want to keep it on the one page. So the key is that you're talking about the difference in the means, in the mean speeds. Since a difference of 0 is in the interval, there is not a significant difference in the mean speeds. Is in the interval. There is not a significant difference in the mean speeds. Nice. These were all boring. We don't have enough evidence to reject H naught. We don't have enough evidence to reject H naught. Let's see if the next one. So remember, the stuff that's italicized is just kind of fun facts, fun platypus facts. You don't need it, although it kind of guides the question. So I guess so they store food in their cheek pouches, kind of like a hamster. And so they kind of like scoop things up and they just carry it in their cheeks, kind of funny. And then they mash it and they eat it that way. They don't have teeth, and so they use the gravel to kind of like chew the food. So they like eat gravel and they kind of chew it that way. Such a funny animal. But you would like to estimate the mean amount of material a platypus stores in their cheek pouches. You collect a sample of 40 platypuses and measure the amount of material each of them store. You find the average to be 33 grams with a standard deviation of 5.3 grams. What type of question is this? It's definitely a numerical data question, right? Because I have a mean and I have a standard deviation. So that's kind of narrowing it down. And I only have one sample, right? I have one sample of platypuses, and I have the mean and the standard deviation of that one sample. So it's a one sample mean type of question. That'll be nice to practice a little bit. We already kind of did it with the paired data, right? It's the same mechanisms, but let's go to our formula sheet. So it's a one sample mean, and we'll just briefly check the conditions. First condition is that it has to be randomly sampled so that we can assume independence. It doesn't say that, and so what do we have to say? We have to say we assume it was randomly sampled. It really just says you collect a sample of 40, right? And so we can say this in two ways. You could say we assume all the platypuses sampled are independent of each other. That's one of the ways to say it. And so kind of option one, we assume the 40 platypuses are independent of each other. Or option two, if you want to talk about randomly sampling still, just to kind of keep the same phrasing as we usually have, we assume the sample was randomly selected. We assume that. Even though it doesn't say it, we assume that it was. And therefore we can assume independence, right? So either one works for me. And our sample size is 40. And that's bigger than 30. So we assume normality. Or I say we can assume normality, which we will. Okay. The question reads, you've heard that they store 30 grams on average in their cheek pockets, but you suspect it might be more than that, right? You found 33, an average of 33. 33 is more than 30, but is it significantly more than 30, right? Is there evidence to support your suspicions? Use an alpha level of 0.01, kind of mixing up the alpha levels. So we have X bar is 33, S was 5.3, N was 40. We want to do a formal hypothesis test, and so step one is to state the hypotheses. From your formula sheet, it's going to look like H naught is mu is equal to mu naught, where that mu naught is the number that I want to compare my sample mean to, right? And so here, this 30, this means my mu naught is 30, the number I want to compare my sample mean to. So H naught is that mu is equal to 30. What we suspect, though, is that mu is greater than 30. So we reflect that in our alternative hypothesis, but because I'm only concerned about one extreme, this makes it a one-sided test. Nice. Step 2. Test. T is x bar minus mu naught divided by s over root n. T is 33 minus 30. We want to know how far is 33 from 30, taking into account the spread, the standard error, which was s over root n 5.3 divided by the root of 40. Well, start there. 5.3 divided by the root of 40 divided by 0.838003. Finally, we get to reject H naught. Why do I say that? 3.5 is huge for a T, right? Anything kind of beyond 2, you start to think, oh, I'm going to reject H naught. So here, 3.5799, 36974. Which also means what? If we think about T in terms of 33 and how far it is from 30, it means that it's 3.6 standard errors above 30. That's really far, right, into the tails. So you can think about it that way as well. Step 3, find the p-value. Or the critical value if you prefer. First, I need the degrees of freedom. Degrees of freedom is n minus 1. That's on your formula sheet, but also we used it for the mean, for the paired data. So I have 39, but I also know here that I don't have 39 listed on the table. So I'm choosing between 39 and 40, and this is where it's important that you go down to 30, right? Because otherwise you're claiming to have a bigger sample size than you actually do. That's bad. But using degrees of freedom equal to 30 in the table, I'm going to try to place my 3.5, 8, or 799 if you want. Let's do that. I put it in the middle, wrapped up in absolute value brackets, just so I can always do the same thing. 3.5799. And on the 30 degrees of freedom line, I move out 3.5. Oof, close. This is somewhere between 3.385 and 3.646. we wanted to do a one-sided test, right? Because I want to know if 33 is significantly more than 30. And so one-sided test, which means I have a one-sided p. So my one-sided p is going to be between 0.0005. Careful with your zeros, 0.001. Or what if you wanted to do the critical value approach? We were told to use an alpha level of 0.01, which means that any t bigger than 2.457, you would reject H naught. So you could think of it that way as well, whichever one you like. Either way, the conclusion is the same. Since the one-sided p value is between 0.0005 and 0.001, it is less than the alpha level of 0.01, which means we have enough evidence to reject H naught. We're rejecting it, we should say, in favor of what? In favor of HA. This means we answer the question, is there evidence that they store more than 30 grams on average in their cheek pockets? Yes, there is. Therefore, I'll kind of rephrase it. There is enough evidence, or there is evidence to support they store more than 30 grams in their cheek pockets. Oh. Terrible. If it's more than 30 grams, this is where it's a reasonable follow-up would be, okay, well, how much more, right? If it's more than 30, okay, fine. But then what is a reasonable range for what they store in their cheek pockets? And that's what the confidence interval is, which, where did I put it? The question here. Here I just pick a random confidence interval, 90% confidence interval. If we wanted to match the results from earlier, right, we would make a 98% confidence interval, right? Because if alpha is 0.01 and we did a one-sided test, I have 0.01 in one tail, 0.01 in the other tail, take those away from one and I'm left with 98. But we can do a 90% confidence interval if we want. So we know the degrees of freedom was one, nope, 39, 40 minus 1 is 39, but using degrees of freedom equal to 30, we want to build a 90% confidence interval. So you could think backwards from, from the one-sided, two-sided P's. You don't need that top line, but I think it's easier. Just go down from here. So then my T star is 1.697. For a 90% confidence interval. Star plus minus T star times S over root N. Again, we've already calculated the S over root N, but it's relatively simple in this case, so I would just redo it. But if you want to store it in your calculator, you can. So we get 33 plus minus 1.697 times, was it 5.3, I think? 5.3 over root 40. .3 divided by the square root of 40 times 1.697, 1.422092075. I'll do 1.42. Because it's already in grams, and so kind of 2 decimal places is good enough. So then I get 33 minus 1.42 is 31.58 up to 33.142. I get 34.42. Again, this interval is all above 30, right? Which matches what we found in the hypothesis test, right? If you kind of think about it this way, 31.58 to 34.42. Well, 30 is down here. So because it's entirely above 30, you have enough evidence to reject H naught that mu is equal to 30, right? So we could still use the confidence interval. We weren't asked to, so I'm not going to, but I am going to interpret the interval. So now, not only do we know that it's significantly more than 30, now I also have a confidence interval for the plausible values of the mean amount they store in their pouches. So we are 90, I'm going to try to not mix that up, % confident. We're 90% confident. The interval from 31.58 grams to 34.42 grams captures the true mean amount stored in the cheek pouches. Any questions about that one? There's a last itty bitty question. kind of a follow-up. And maybe I'll discuss what it means to make a type 1 and a type 2 error in the previous question. Oh boy, it's been a while. Type 1 error is when we reject H naught when we shouldn't have, right? And so a type 1 error, just as a, is when we reject H naught but shouldn't have. And the type 2 error is when we fail to reject H naught, but it should have been rejected. FTR failed to reject H naught, but should have rejected it. What this means is if you've rejected H naught, there is always a probability of making a type 1 error. If you fail to reject H naught, then there's always a probability that you're making a type 2 error, right? And so a type 1 error is, in this case, concluding that they store more than 30 grams in their cheek pockets when they don't. All right. So in this case, type 1 is concluding they store more than 30 grams when they don't. Or when they actually store 30. Maybe I'll clarify that. When they actually store 30 grams. Try to keep it on one page here. Whereas a type 2 error in this scenario would mean, okay, a type 2 error is when I don't reject H naught, but I should have, right? So that would be saying that they store 30, but they actually store more than 30, including they store 30 grams, but they actually store more. Difference between those two, or the potential errors that we could be making, are not a big deal, right? But if we think about kind of important things like, do you need to tear down this building and build a new one? Well, concluding they need to tear down this building when they actually shouldn't, that's bad, right? Or saying, nah, you don't worry about it, you don't need to tear down this building, but they should have, that's also bad, right? So depending on kind of the gravity of the conclusion, in this case, doesn't matter. Oh no, it was more than 30. Oh well. But yeah, so just keep an eye out for those type 1, type 2 errors, and I'll throw them on the test. How about something about it? All right, that is it, and kind of worked out nicely. If you have any questions, let me know. Otherwise, I'll see you on Tuesday for the test.